Did you know that the ocean covers more than 70% of Earth's surface? Its existence is crucial to sustaining life as we know it. Nevertheless, the ocean remains an underexplored resource, with about 80% of it to be discovered. The ocean is also the largest reservoir of heat and carbon dioxide, having absorbed about 40% of the carbon dioxide generated by humans since the Industrial Revolution. As climate change progresses, the level, temperature, and acidity of this big blue world are increasing at worrying rates, as the last report of the World Meteorological Organization states. The consequences of these alterations can be devastating for many different ecosystems. It is important to expand our knowledge about the ocean and how it can help us in the fight against climate change. Interestingly, we might have to look up to the space and then look down from it to understand the ocean. But how? That's what we're going to find out in today's episode, so stay tuned. Hello, and welcome to another episode of Crosstalks. My name is Adriana Costa, and I will be your host. This podcast series by the UT Austin Portugal Program will walk you through the wonders of science-business collaboration. We will be exploring emerging topics in advanced computing, medical physics, nanotechnologies, space-Earth interactions, and technology innovation and entrepreneurship, as we delve into the program's industry-driven research projects. After the launch of Sputnik 1, the world's first artificial satellite, several others have followed, and nowadays there are currently around 3,000 active satellites of all shapes and sizes. Satellites revolutionize how we communicate with people on the other side of the world, predict the weather, and research space, Earth, and oceans. To study ocean level variations at the local, regional, and global level, UT Austin Portugal's MAGAL Constellation project uses satellites that fit in the palm of our hands, called CubeSats. Since teamwork makes the dream work, MAGAL plans to create a constellation of these small satellites to work together as a system and acquire data with global coverage. Although small, they will play a significant role in the measurement of oceanic data, gravity, temperature, and salinity. And that is why MAGAL is equipping those satellites with the next generation of radar altimeters. What are radar altimeters, and how can they help study our oceans? Can the data retrieved help minimize the impact of climate change? To answer these questions, we invited Arlindo Marques, Product Manager of the Aerospace Department at Efacec, Clara Lázaro, Assistant Professor at the Faculty of Science of the University of Porto, and Interdisciplinary Center of Marine and Environmental Research, Paulo Figueiredo, Data Scientist at Center of Engineering and Product Development, all in Portugal, and Brandon A. Jones, Assistant Professor at the Department of Aerospace Engineering and Engineering Mechanics at UT Austin. With the combined efforts from businesses in Portugal and researchers from UT Austin, we will get to know how this project is at the forefront of ocean studies. So welcome, Arlindo, Clara, Paulo, and Dr. Brandon, and thank you for joining me today.
Welcome, thank you.
Thank you very much for inviting me for this podcast.
Thank you.
Let's start by exploring the name of your project, MAGAL Constellation. We are used to think about constellations, but in this case of stars. However, you aim to create a constellation of satellites, and I want to ask Arlindo what you are studying with these constellations, and also, can you summarize what this project consists of and how it came about?
Portugal has a huge maritime area, bigger than the land area and its scale. And according to the new European directives, we shall monitoring them and focus on them in the next in coming times. We are talking in the last years and the last decade, and it's a hot topic at the moment, the climate change that we are facing, and no one has doubts or they are occurring, although the different analysis and the places they can evaluate them. But look into the oceans and study their variations locally regional or globally, it's one of the best ways or one of the inputs that we can use to study this change and evaluate the climate change. Since Portugal has this huge maritime area, protected area, that we shall also look to them and focus our research on them, and profiting the new the source that Portuguese is developing in the space sector. This brings a boost to the sector in Portugal, and we were able to join the Portuguese industry and academy together with this UT Austin program to develop constellation of satellites to monitor the oceans, not only in Portugal, but also globally and study this climate change. We can synthesize the objectives of MAGAL in 3 segments or 3 areas. We have scientific objectives where we want to involve the Portuguese Academy in studies of the ocean climate change and create knowledge and also new algorithms and processes to this area. We have objectives at the engineering and technology level, where we want to push the Portuguese industry to create competencies in the space market, especially in this new space segment of small satellites, where MAGAL satellite shall be at the end a state-of-the-art radar altimeter, very small, with improved temporal and spatial resolution compared with current available missions. And we also have the objective at the entrepreneurial and business level with development of a new concept of data center, where we shall gather not only the MAGAL data, but also combine it with other sources data from different sources, from gravity to temperature, ocean temperatures, tides, salinity measurements, other satellites, putting all together and implementing or creating products and services to the end user with added value and more complete ones. In order to achieve these objectives for MAGAL, we have set or we have defined a set of use cases and also associated service products as priorities on it. Our use cases are mainly the sea surface topology, either at local or regional scales, eddy detection and tracking, marine debris monitoring, inland water levels, and the associated products or primary products and service that we want to provide to the end users, fisheries in local and regional area, by providing higher temporal solution, which can be used to improve the roads and navigation for fishing. The marine protected areas monitoring, following the new European requirements directives that we can, with this constellation of satellites with higher temporal solution, provides a better monitoration and information. And also it can be used to monitor natural disasters, also based on this better temporal resolution. So summarizing, we will look with this constellation of satellites to the oceans. We will measure its level, average level. We will then merge these measurements with other sources of information in our data center to provide a product to the end user with aggregated added value for the consumer.
Thank you, Arlindo. It's very interesting to see how many things you can do with this project. Now, I want to ask Brandon, why exactly choosing to create a constellation of satellites? And what are the advantages compared to the use of a single satellite?
So constellations of satellites, just in general, before you even start talking about small satellites, they allow governments, businesses, whoever is interested in achieving some sort of objective to use a mission concept that just frankly is not possible with a single satellite. So let's take an example, the Global Positioning System, or GPS, right? This is a constellation of satellites that is critical to our modern society. Can you imagine if the GPS constellation disappeared for 10 minutes? I mean, we'd have a breakdown in infrastructure. It's so critically important to society today. And this is achieved through a constellation, in this case, almost 30 satellites in Earth orbit that allow us to be able to determine where we are with a phone or our cars to autonomously drive, et cetera. So this is amazing what can be achieved, but it doesn't stop there. There are other constellations like the GRACE mission, which use 2 satellites to map the Earth's gravity field. And they use that to be able to study and understand variations in the rainfall in the Amazon or changes in the sizes of ice sheets at the Earth's poles. So constellations allow you to do things like this: communications, satellite-based internet services that we have now. So this is all very remarkable that can be achieved with a collection of satellites. And now with something like MAGAL, we could improve our understanding of the Earth's oceans.
Thank you, Dr. Brendan. I don't know if Clara wants to add anything.
Since the development of satellite altimetry, or this new era of satellite altimetry, I mean, since the 90s, the development of satellite altimetry has been steady, and an effort has been made by the international scientific community to provide or to guarantee data continuity. Since 1991, we can say that we have 2 different series of missions. The first one is, well, a continuity of missions of NASA's responsibility. NASA and also the French Space Agency. And the other series of missions is of the European Space Agency responsibility. So, and these missions can be thought of as being complementary, okay? So, since 1992, we have data acquired by Topex Poseidon, the Jason series of satellites, and the operational mission, the current one, which is the Sentinel-6 Michael Freilich, which have been essential to monitor sea level variability, and they have already provided nearly 30 years of data, okay? So these are the most precise missions, and they sample not the global ocean, only between minus and plus 66 degrees latitude in, let's say, 10 days. The other missions cover the ocean, the global ocean, and also the polar regions in 35 and nowadays 27 days. So the idea is that the reference missions, those that sample the ocean each 10-day period, are the most precise ones, are the reference missions to which the others should be calibrated to. Missions like ERS-1, ERS-2, and now Sentinel-3A and B cover or observe the whole ocean in, let's say, 27 days. So we must understand that there are technical constraints that force to not be able to improve the temporal sampling of the ocean and the spatial sampling of the ocean simultaneously. For instance, all satellite altimetry missions are launched into exact repetition orbits. This means that their orbits will repeat after an integer number of days. This integer number depends on the mission. So for the reference missions, this number is 10 days. For the complementary missions was 35 days and now is 27 days. The shorter the repetition cycle, the larger the spacing between adjacent tracks of the missions. This is because these conventional or even SAR missions only acquire data along the satellite's ground track, okay, well, ground tracks. This means that we have ascending tracks, descending tracks, they will cross over, and we will have diamond-shaped regions of the ocean without no data. So in order to decrease these regions of no data, we need to combine missions with different characteristics. So the basic idea is to use, for instance, the reference missions to study sea level variation, okay? And in order to have a cyanotic view of the ocean, improving the spatial sampling or resolution, if you prefer, we need to merge data from several missions. Therefore, if we have more data, more missions, acquiring data over different ground tracks, we can combine all this data and increase the spatial resolution. Okay, the best temporal resolution that we have nowadays is 10 days. Okay, so the reference missions observe the whole ocean in a 10-day period.
Thank you. It is impressive how these type of systems and constellations are used for things that we consider nowadays to be essential, like GPS or the internet. We can't stop to think about what is involved for us to have all the information we want at our fingertips. And also it is very interesting to understand how different missions need to work together so that we can have better data. Clara has mentioned altimetry. I would like to ask, in this project, you have equipped these small satellites with radar altimeters. What does a radar altimeter exactly do? And how can it measure the oceanic data you propose to study?
Radar altimetry is quite simple. I believe it requires, however, a remarkable precision to accomplish. Let's say that the altimetric measurement is made by sending a radar pulse from the satellite, or the altimeter antenna towards the Earth, towards the surface of the ocean in the radial direction, okay? And what is done is measuring the amount of time that the pulse takes to make the round trip from the spacecraft to the ocean surface and back to the spacecraft. I mean, the pulse is reflected by the surface of the ocean and it is sent back. It's the echo of the pulse, okay? So since the signal travels at the speed of light in the vacuum, however, it is assumed in order to perform the first calculation. So we need, the first requirement is that we need to have a very precise measurement of this round trip time, okay? So for each measurement, we need to know the position of the satellite in its orbit. For us, it is important to say that this position should be as accurate as possible. So by knowing the position of the satellite in a terrestrial reference frame, this means that we know the altitude of the satellite, of the center of mass of the satellite, of course, above the Earth's ellipsoid. Therefore, by subtracting from this altitude the distance, the range measured by the altimeter, what we have is the surface of the ocean above the same reference ellipse, or it's an ellipsoid, okay? It's a mathematical model of the Earth, let's say. So the position of the satellite, in order to be known accurately, we need to have on board several or different space geodetic techniques for positioning, okay, like global navigation satellite systems, radio ranging, laser tracking, and so on, okay? So basically, we have at each location, usually provided with 1 second rate, okay, measurement, we know its location, okay? Since these orbits are repeating each n day period, it means that after n days, we will have another measurement over, not exactly, but as close as possible measurement for the same location. If we average over time all these measurements, these instantaneous measurements of the sea surface height above the reference ellipsoid, we have the mean sea surface. Okay, so for the first time with satellite altimetry, we were able to have a picture of the mean sea level globally, okay, because until then we only had I don't know, mean sea level at coastal locations measured by tide gauges, for instance. So if we subtract this average value at each location, we have what we call the sea level anomaly. And we can, this is the, I would say, well, I'm biased, but I would say that it's the most important variable that we can extract from satellite altimetry. So we can analyze how the sea level anomaly varies with time, okay? For instance, we can compute the global average of sea level anomaly for all locations and plot this average with time. Then we will have a time series of satellites of global mean sea level. And we can look at this time series and understand how global mean sea level is changing, okay? And it is nowadays known that sea level, global mean sea level is rising. Well, it is not only rising, but it is also known currently that global mean sea level is also accelerating, okay? And from satellite altimetry, we know since 1991 that global mean sea level is rising and that we should account for 3.5, depends on the study group, scientific group, but between 3.2, 3.5 millimeters per year, okay? We also can analyze this time series of sea level anomaly for each location. And we can have a picture, of how sea level is changing, not only globally, but also regionally or even locally.
Thank you. It was a very well explained way to understand a little bit more about radar altimeters. Going a little bit back, MAGAL is developing a constellation of satellites, but not only that, it's a constellation of small satellites, which are called CubeSats, to study these ocean level variations. I want to ask why choosing such small satellites and what are the major differences between or compared to conventional satellites?
So the economic principle of economies of scale, it kind of relies on the generation of more output for an enterprise to produce a profit, right? So when I say profit, it could be financial, but in our case, it's also scientific gain. How do we maximize the information that we're able to produce? So for the commercial space industry, really to become cost effective, it must provide services that produce enough useful data. And in order to do that, you need more satellites. That's where the constellations start to come in. But that starts to get expensive. It is not cheap for one GPS satellite to go up into orbit. That's why you need governments like the US federal government in order to do that. But CubeSats allow for achieving a larger output than what you get with these larger satellites. So why is that? So the primary cost to build and maintain a constellation of satellites is launch, actually taking it from the Earth and putting it up into orbit. So when launching a satellite, a rocket that you put it on, it's able to launch a certain amount of mass up to a given altitude. So these larger satellites, whenever they are sent up there, there is some mass left over, right? That they get it to a certain altitude, but they don't use up all of that mass. There's a little bit left over that they didn't use. So for a small fee, you can include multiple small satellites, and we standardize this into what is now known as a cube satellite. So it makes it easier and cheaper for companies to do this. And this process, we're using this small fee to put many cube satellites to fill up this extra mass, is known as a ride share. And this has created this kind of new space economy where it's cheaper for businesses to put satellites into space. They kind of piggyback on these other larger missions. And this is not a small number of satellites. So for example, in 2017, India deployed 104 satellites in a single launch. And this was the first of its kind. Since then, SpaceX is now launching more than 50 satellites every 2 to 4 weeks using this paradigm. You know, this has changed the approach to how businesses can approach their model for access to space. So compared to large satellites, a small satellite is cheaper to get up there, but it's not without its disadvantages. It is naturally smaller. It has less power, it has less mass, it tends to have less compute capability. So this creates some engineering challenges that require miniaturization. How do we take what used to be a large satellite and turn it into a small satellite that, as you described earlier, can kind of fit into the palm of your hand? But once you do achieve that miniaturization, the economy of scale starts to come back in, that I can now build the multiples of these satellites. It's not this large cost for one. For a constellation, if I figure out how to make one, I can start to build 3, 4, 5. And you start to have companies like SpaceX and OneWeb that literally have assembly lines for these cube satellites at this point. So it's changed how we can approach the building of platforms like this.
Thank you so much for your response. It's very interesting how this is not only on the scientific level, but also on it reduces costs and everything else. And I know it may be challenging to try to optimize everything that you would have on a big satellite into a small one. I don't know if anyone else would like to add anything.
In our case of MAGAL, we are designing MAGAL to have the minimum payloads required to perform the science that Clara already described, even the accuracies defined for MAGAL, which are in line with current missions and in same orders of magnitudes. So we intend to deliver a constellation of satellites to perform ocean monitoring with similar accuracies, with increased or higher temporal resolution, with similar spatial solution, but with a lifetime lower than current available missions. Okay, this brings other discussions that we can talk later, but it's also a low cost option, which can even be profit. Instead of having just a single constellation, we can have several constellations which will provide more data, and with more data, surely science will provide better information, better analysis, better end user services.
And so we have been talking about data collection, and I would like to mention one of the other goals of the project, as Arlindo has said earlier, which is the development of a data center for the end user services interface. And I would like to ask Paulo Figueiredo, which services and data will you make available to the end user, and how will this interface work?
Yeah, sure. To answer that question, we need to understand the Portuguese context and the purpose of a data center. In Portugal, the blue strategy involves the extension of the continental shelf, since the understanding of the sea is expected to leverage both existing and new sea sectors like economy, like environment, safety, tourism, and so on. However, this whole process involves the acquisition of high data volumes from several sensors, from several platforms, from public entities, and so on. And the big question here is how to get data from the sea, how to store it, value it, and how to make it sustainable. Some of these questions do not have an easy answer and are already documented by several entities, for example, the United Nations National Sustainable Development Goals. MAGAL project here intends to acquire, value and exploit the high potential sea remote data from MAGAL Constellation, like already said, the sea surface height, mean sea surface level, etc., with other public data, for example, meteorologic or other sea data from the constellation, like, for example, complemented with, for example, the information from Copernicus program and so on, in situ data, etc. However, in return, dealing with these big data issues raises specific issues like volume, velocity, variety, veracity of the data, and value. These are known as the big 5 V's of development of a data center. So the data center in MAGAL project must be a platform built for the upcoming years for simulated activities ready to supply several users, built with the latest technology, answering typical 5 V's, like said previously. And while previous data centers were only used to act as repositories, and nowadays these data centers are very complex systems, since they must be capable of processing, storing, and transmitting the digital information. The platform data analysis center developed during this project, MAGAL project, will allow an easy and intuitive access to data in different maturity levels. The platform considers a service-based architecture, a microservice-based development capable of what? Receiving data from several sources in different formats and different types, different quality from different partners, provider later, different products to different customers or stakeholders. And the platform will follow a typical software well development, meaning that we'll have a backend, that there is the data acquisition from several sources, a typical ATL, the extract, transform, and load the data to ensure that the data is valid and it will be useful. And then the part of the intelligence, that will be the application of AI models, artificial intelligence models, machine learning, deep learning, etc. The part of data science, and then a front end, that part that is the web dashboard of the interface. The final users will be capable not only of having all the data on a single platform from anywhere in the world, but will be capable to correlate different layers from the data from several sources using simple and complex models over the data. One other important consideration it is that it will be capable to deliver specific data to specific users according to different users' permission. And this data center will have 4 main maturity levels. From level 0, there is the raw images, to level 2, there is MAGAL products like sea surface height, sea level anomaly, mean sea level surface, mean sea level, mean sea level. To level 4, there is the correlation with the other sources of data from the other platforms. With this information, we can open the information so we can have more data and to have this information all into a single platform.
Thank you. This idea seems very, very interesting. I would also, just out of curiosity, who would be able to use this data center? Would it be available to everyone in general, or for industries who would have access to this data center?
That is a great question, because all of them are expected to have the access to the data center, meaning that we will have data. We'll act as a, for example, we will acquire data from Copernicus and we'll make it available to users. Okay, so they can download it. We'll have a link to the data hub, so they can acquire the data. However, for more specific data, it will be after processing the data according to each user's permission. You'll have access to higher levels of data or lower levels. For example, in terms of partners of the MAGAL project, they will have access to all of this data. But for example, for a commercial use, a commercial purpose, you will have a fee, so they will purchase this type of data in order to do their business. So it will be available for not only for research, but for commercial application as well.
Okay, thank you. That clarifies a little bit more about this data center. This project and its construction leads for me to question something that is a problem that the space science community has talked about, which is the space debris problem. Since there are more than 3,000 inactive satellites orbiting the Earth, and since we are creating a constellation of satellites, which involves many different types of satellites that go around the Earth, I'd like to ask if MAGAL plans to minimize the problem of space debris, and how can it do so?
Yes, MAGAL is considering and is not it's considering space debris and this problem from the beginning. So currently there are already settled and they are starting to be put in place some European directives about these low orbit new satellites in order to take them out of the orbits at the end of life, to release this area or these very dense populated orbits. As Dr. John said, we are launching tens of satellites every month, and we are getting crowded there. So basically, these European directives states that these satellites shall re-enter the Earth atmosphere even 25 years after its mission completion. So MAGAL as CubeSat will fly in low orbit, so low Earth orbit, and is planning to have a 3 years life. After these 3 years of life, MAGAL shall be decommissioned by deorbiting, so meaning that it will lose altitude and it will re-enter at Earth atmosphere, where it shall burning up during that process, and no debris shall remain from the satellite. So for us, as MAGAL designers, we are trying to design it to live, let's say, in a clean space with no debris, taking or having placed requirements from the very beginning of the project for its commissioning of satellite, and all these phases for the commissioning, meaning the demise phase, that satellite self-fragment in a desired way. So it's a predictable way how the debris are lost or fragmented from satellite during the re-entrance into Earth atmosphere. Also the passivation process by discharging batteries or minimizing the risk of explosion are being taken into account or are being considered in the MAGAL design.
Thank you. It's really interesting how the project also has taken into consideration this problematic. Now I want to talk about the consortium that is a part of this project, which is one of the program's largest consortiums, bridging industries, universities, and research centers from Portugal and Texas. What strategies have you used to manage a consortium this big, and especially when travel and access to laboratories were severely constrained due to the pandemic?
That's indeed a good question, because as everyone knows, it was a huge challenge at the very beginning of the project in the middle of 2020 when we started this project. So as you know, we were starting living a pandemic situation, which creates, with the size of the consortium, creates a huge turbulence in the slow start of the project. After some time and some adaptation to this new lifestyle, let's say, we start using digital tools, we start communicating each other, we start aligning and positioning and meeting offline through the digital tools, like we are performing this podcast today. And also we have a great commitment of all partners to do or to work more autonomously with the closest supervision and the synchronization of information between all partners. For that, basically, we have established weekly meetings. We have established shared points accessible and shared between all partners. We have created this SharePoint with repository of all the information, all the data, all the reports, critical and for project, where everyone can see what are the achievements, what are the decisions, where we have also minutes of all the meetings to see what were the decisions the parties chosen and so on. With the time, these last 2 years of pandemic situation, we were starting getting using to these digital tools. And nowadays, I would say that even for meetings that sometimes we can do presential, we already do it online just to save the traveling time and the profiting these technologies. Regarding organization of the works, mainly we have a big consortium, but we are more or less well defined frontiers for activities of each works. Nevertheless, all the other partners knows what the others are doing, knows their outputs, knows their options in advance, and follows their progresses. Basically, in the MAGAL project, we although we have industry, academy, and institutions partners, we are mainly considering two types of partners. Here, the science partners and the industry developers partners, mainly in these two areas of working. On science partners, we have all the academies and we have mainly some institutions like CIMAR, Air Center, Plus Atlantic, University of Açores, which under MAGAL take the lead of the defining or performing the bridge between science, the pure science, and the services, and what shall we do with data, to the industry and the developers of the equipment or satellite itself. So these science partners take the definition of the satellite or the mission use cases, which process, which services, which algorithms we shall apply to the data acquired by the satellite to create and deliver the products to the end user. On the developing part, here we have a more division of the works. We have, say, performing or leading the activities related with data center and also the 3D satellite design and integration, putting all the payloads that we need to perform or to achieve to complete the mission of MAGAL into a single satellite. We have working together in the propulsion system and defining the orbit and studying the best options for the MAGAL's constellation, Omnidia, and the University of Beira Interior, to develop and implement the breadboard of the radar altimeter. We have Efacec and UT Aveiro working together on this payload. Then we have Instituto Superior Técnico in Lisbon, mainly working in the business plan regarding the technology assessment and the market opportunities and economic impact that MAGAL can bring or introduce to the sector with this definition. All of us, Portuguese industry and academy, are having here to support in all areas of knowledge and expertise from University of Texas, Austin, which is acting more as a consultant to us, supporting all the activities and reviewing or complementing the information whenever we need their support.
You are in the last year of completing your project. At the end of it, where do you expect to stand in Portugal's new economy of space? And how important has the cooperation with UT Austin been to get you there? And what is the path forward to get this constellation back in downstream applications and services?
That's another good question. As you know, MAGAL aims to set a new concept of doing radar altimetry. So we aim to have a constellation of small satellites to monitoring the oceans. The goal of the MAGAL project is to define architecture, define a design for this constellation, analyze the design, study, and conclude on its performance, its feasibility, and its implementation from the practical point of view. Nevertheless, MAGAL project doesn't foresee the real implementation or the real manufacturing of satellites themselves. So one of the major next steps for this project surely is the moving from the conception of the constellation design that we expect to have at the end of MAGAL and go to the next step, manufacturing and performing a real field test with, I won't say the full constellation, but at least one or two satellites just to demonstrate the concept and demonstrate the performance of MAGAL design satellites. Up to now, and under the MAGAL project, we have already achieved several results of the project. We have established minimum requirements to perform or to design such a constellation. We have implemented a business plan. We identified use cases, products to be explored. We have defined the full architecture of the satellite. We have identified all the payloads. We have selected baseline payload from the market to perform that function. And we are now doing the integration and 3D design of the satellite itself, consolidating the interfaces and compatibilities of those payloads is one of the tasks that we expect to conclude in this last year of the project. The data center, as well as all its requirements, all its architecture defined, all the algorithms and products are identified and implementation is ongoing on this side. The critical payload for this MAGAL constellation, that is the radar altimeter, we have finished this summer the breadboard of it. We have performed the first and the preliminary field tests with a good match between the field results and our simulations, which it's indeed excellent indicator on the performance of the MAGAL constellation. On the radar altimeter, we still have an open point that is indeed one of the criticalities in our design. That is the radar altimeter antenna. We are looking for a deployable antenna, and from the available options, we are getting quite spread budgets on this equipment, which we are trying to contact manufacturers and consolidate this system. But I would say that we will be successful also here in concluding this topic. Also, in these 2 years of the project, MAGAL has published several papers and attended several conferences. We have also performed our first workshop where we have presented the MAGAL project, and we present the objectives and our view of the architecture and what was the planned performance of the MAGAL were presented to the stakeholders and the potential end users, where we get also some feedback from them. And basically, it's the status of what has been achieved up to now and following the steps for MAGAL that I would say we shall look for a follow-on project of MAGAL to manufacture this constellation and goes for a field trial. Here, the partnership with Austin has been essential because all this sector is quite new for all the Portuguese industry. We have a lot to learn, and it's always good to work with an experienced partner that we know that are on our back supporting us, and whenever we have doubts or we have to choose one path in the frame of several ones, we can inquire and we can count with UT Austin support, providing or helping us establishing the pros and cons on those paths to decide and to choose the best solution for the project.
I'm glad that MAGAL has been able to accomplish the goals for the project, and I hope that the project has a future for the years to come. And that's all the questions I have for you today. Thank you all for your answers. They were very enlightening. Is there anything you'd like to add before we finish?
Just a final remark, I would say that MAGAL, as was presented, is a proof of concept. So MAGAL is an innovative concept for radar altimetry that was never implemented before. So MAGAL aims the definition and implementation of a constellation of small satellites based on radar altimetries to monitor the ocean's levels, which can improve on-orbit capabilities at reduced costs for ocean monitoring and climate studies, and in this way redefining the radar altimetry concept. MAGAL Data Center is also an innovative approach in the sense that it will aggregate not only MAGAL data, but also data from other sources to improve and provide a better final product. If we have more data, more data as far as they are reliable, it's always better to perform science.
Interesting to see how we can combine all the efforts of many different people who dedicate their lives to this, and how it can impact the lives of many people in the years to come and even generations. With that said, I want to thank you very much, Arlindo Marques, Clara Lázaro, Paulo Figueiredo, and Brandon Jones. It was genuinely nice to chat with you today and learn more about your project, and we wish that your results can have an impact on society for the years to come, and especially regarding the challenges that we are currently facing, for example, climate change, ocean level variations. We hope that MAGAL can play its parts on solving these issues.
Thank you for the opportunity for presenting MAGAL, and surely we expect also to fulfill that goals.
Thank you very much for the opportunity and for the attention.
Yes, thank you.
Yeah, thank you, Elsa. Thank you.
Thank you all for listening to this episode of Crosstalks. If you have enjoyed it, and even if you did not, we would love to hear from you. So make sure to subscribe through your favorite streaming platforms and leave a review. For additional content, follow us at UT Portugal on Twitter or visit utaustinportugal.org. MAGAL Constellation is co-financed by the European Regional Development Fund through Compete 2020 and the Portuguese Foundation for Science and Technology, bearing the seal of UT Austin Portugal. The total eligible investment is around 2.6 million euros, with public funding amounting to 2.2 million euros. UT Austin Portugal is a partnership program in science and technology between the Portuguese Foundation for Science and Technology and the University of Texas at Austin, supported by the Ministry of Science, Technology and Higher Education in close collaboration with the Council of Rectors of Portuguese Universities.